Hey, what's up guys? Welcome back to another episode in the Deep Learning with Tensorflow series. In this video, I'm going to teach you guys about data augmentation. Data augmentation is a way of artificially increasing the size of your dataset by doing transformations on the data that you already have. So we're going to be focused on data augmentation specifically for images since right now we're doing convolutional neural networks. But here's an example of doing transformations to an image like a cat, for example. We can take a cat and then flip it. So it's upside down now. We can rotate it in different ways. We can blur it so it's less clear. We can change the exposure. We can change the contrast. We can make it grayscale. These are just a few different ways that we can augment an image. It's simply changing the image in some way. The idea though is to simply create more variations of the data that you already have, like this cat here. It's a great option to employ if you have either a small amount of data in your dataset or you just want more variation in your dataset. The primary effect of data augmentation though is that since you generate more variations of these images, it can help prevent your model from overfitting. Therefore, it's another regularization technique. And I think intuitively this kind of makes sense. If you have an image of a cat, for example, and you apply a bunch of transformations like this, the model can learn what really makes a cat a cat. As long as an image has the features of a cat, the model should be able to identify it. So therefore, giving more robust examples of the images of your dataset makes the model more robust and therefore able to generalize a little bit better. Hopefully that makes sense. So you're creating more data in your dataset by taking the data that you already have and augmenting it in different ways, but that also has the effect of fighting overfitting because that can enable your model to generalize better. So the way I'll be teaching this concept in this episode is using the TF flowers dataset. It's the Tensorflow flowers dataset. It's just a dataset within Tensorflow that has a bunch of flowers. There's about 3,600 flowers total, split into 5 different classes such as tulips, sunflowers, roses, dandelions, and I believe daisies as well. Here's an example of just a few of these images. So this data set is not really very large. It's only 3,670 samples in total, which is crazy, and you also have to split that into a training set and a test set. So therefore, this data set is probably a good option for data augmentation because there's not a lot of data already in it. So data augmentation can produce more data in the data set, but also at the same time, we can help the model generalize better because we can have it see a tulip, for example, in different ways than just this perfect shot right here. And I'll give one more example because I just really want this to make sense. If you have a data set with a bunch of images like this that are just completely perfect, you have a cat that's, standing straight up, he's looking at you, it's very clear, and that's all of the images of your data set, they're just like that. That's probably not going to translate well to the real world because in the real world, you're not going to be able to take perfect images all the time. If you're going to make an application that can, maybe it's an app on your phone that scans animals and tells you what they are, these animals that you take pictures of are not going to look as perfect as this. So ideally, you want to create a bunch of images that don't look as perfect and just create a lot of variation so that no matter how it sees a cat in an image, it can hopefully recognize it a little bit better than otherwise. So that is the real power of data augmentation, and that's what we're going to get started with. We're going to start by training a classifier that can recognize flower types without data augmentation, and then I'll be showing you guys how you can add data augmentation using TensorFlow and using Keras so that you can improve the results of your model. So let's get started. All right, here's some code. So we're going to start by importing the flowers dataset from TensorFlow. So we're just going to do TFDS, which stands for TensorFlow datasets. So we're importing TensorFlow datasets as TFDS. Then we're going to load in the TF underscore flowers dataset. And this will just tell it, as you can see, the split between the training set, the validation set, and the test set, which will be this, this, and this. And we also have with info, so it'll also give you some metadata to take a look at. Setting as supervised to true, just make sure that we have the correct format. So for every sample or instance of these different sets here, it'll be a tuple that has both the image and the label. We also have this piece of code here that's going to use our metadata that's given to us when we load the dataset, and it will just simply get the number of classes that we have available in this dataset. There we go, we can see that we have 5 classes, which corresponds to tulips and dandelions and stuff like that. Next, what I like to do is just take one of the samples and just visualize it so I can see what kind of data we're working with. We've already seen a couple of examples in the presentation, but here it is in our actual notebook. So we have some tulips here, and so the label 2 stands for tulips. So to be clear, these are not NumPy arrays like we usually have when we load datasets from Keras. This time, since we're loading our dataset directly from TensorFlow as a TensorFlow dataset, this is giving us an actual dataset object to work with. So this is a training dataset, a validation dataset, and a test dataset of the type dataset from tf.data. So that's why when we need to load a single sample, we have to do this piece of code here. So we're simply taking one from our training dataset. We're taking one and then using this piece of code here to actually access it and extract the tuple. So we're getting the image, we're getting the label from that, and then we're showing it. Here's the next piece of code. So this is a lot, but let me just break it down for you. So first of all, we're going to start preparing our data set. What that means is that we're going to be batching it, shuffling it, all that kind of stuff, right? What we're going to make is this function here called preprocess, which is going to take an image and a label and just simply do a few things to the image. So we're going to resize the image to a standard range of 256 by 256. This is because all of the images in our dataset are not the same size. But when we feed images into our neural network, we want them to be the same size because the neural network expects that. They have to have the same spatial dimensions, right? So all this will do is simply resize the image to be 256 by 256 if it's not already. We're casting each of the pixel values to a floating point number instead of just an integer, and then we're dividing it by 255 so that it's within the range 0 to 1. So we're going to take this function and apply it to all of our data sets, so our training set, our validation set, and our test set by using our map function that we learned about before. If you haven't seen the video I made about tf.data, make sure you check that out because it explains all this stuff here. So we're going to map it by calling map, passing the function we're going to use to map it, and then this little piece of code here was added, which will tell it how many parallel calls it can do, which can, make it run a little faster, use parallelization, and then having it auto-tuned will just have TensorFlow choose the correct number for this parameter here, okay? So after we map the data in the data set using that function to make sure that it's standardized and normalized, we can go ahead and do other stuff like batching. So we can call batch, pass in a batch size, which we're going to set to 32, that's the standard number. And then we can also prefetch by whatever number TensorFlow thinks is best. And all prefetching is, just as a little reminder, is that when your model is training, TensorFlow can start loading and preprocessing the next batches that will be fed through the model. That way it can execute a little bit faster and more efficiently. Also in the training set, we're calling .shuffle just so we can make sure that the data within the training set is shuffled because that's ideal, of course. When we have batches of samples within a training set, we want them to be not all of the same type. We want them to be a bunch of different types mixed together, obviously, right? So shuffling it is a good way to do that. After this, we are then defining the actual architecture for a model. This is a convolutional neural network that has 3 convolutional layers followed by max pooling layers that will have the spatial dimensions because they're 2 by 2. We start off with 32 filters in the first convolutional layer. It has an activation of ReLU. The input shape is going to be 256 by 256 by 3. This is because, of course, we resized every single image to be 256 by 256. So that's the spatial dimensions that should be accepted or expected. And then 3 is because we have RGB images. These are colored images. So then we go to 64 filters, 128, another max pooling layer. Then we flatten it. And then we actually feed it to the classifier part. So we have a dense layer with 256 neurons with an activation of ReLU. We have some dropout here just to hopefully improve the training process. And we have a softmax activation on the last output layer just because we're doing a single label multi-class classification problem. So this part as a whole should be a little familiar. That should all make sense. Then we're compiling it same as always. And then now we're actually going to train the model. So we're calling train, we're passing in our training set, we're passing in our validation data with the validation set, 50 epochs, that's a lot of time. And then we're doing an early stopping callback with the patience of 5. I changed the patience to 5 just because I noticed that when I'm training my models, sometimes I have a too low of a patience because I can see that the performance of the model is trending downwards in the correct direction, right, in terms of the validation loss, but it cuts it off because the patience is too low. So I just upped it a little bit. The last thing I'll do is add this part of code here, which will plot the accuracy and loss just like always, and then also evaluate the model on the test set. But that's it. Just to be clear, we're not doing any data augmentation at this point. Let's just see what kind of results we get, and then we'll add it after that, okay? All right, here's the results. It finished training after 8 epochs, and we can see that it starts overfitting pretty quickly, almost right away actually. And we can see that on our test set, we have an accuracy of about 64%. If you retrain this a few times, you'll see better or worse results. I've seen 65% and then like 84 in loss. So it varies. But the thing though is that if we add data augmentation to this, I'm able to get it up to a accuracy of 77%. Like that's crazy. That's a huge increase in accuracy just by changing the variation of the data, by augmenting the data. So we're going to see how we can do that now. So there's actually, just like everything, a few ways you can do this. We're going to learn how we can do it with Keras within TensorFlow, because that's what we've been using for almost everything. So the way that you do it is you create data augmentation layers, just like we do with our sequential model here. But the thing is, you can either add that directly to your model and the data augmentation will run on the GPU, or you can run it before the data is fed into the model and that will run on the CPU. So you can either integrate it into your data preprocessing pipeline, or you can integrate it into your training process directly. I'm going to add this at the top here. So we're going to start with data augmentation is equal to, and now we're simply going to use sequential. So we're going to make a sequential model, except it's just going to be, it's not a model itself, it's just going to be a bunch of layers that we can either, like I said, put in directly into our model or add to our preprocessing pipeline. So the data augmentations that we want to do are just simply layers within Keras, which is very convenient, of course, right? So we could do stuff like layers, dot, and we could do random flip. So this will flip the image in different ways. So we could do like horizontal, for example, horizontal, spelled wrong, horizontal, or you can do horizontal and vertical. So as the name says, this will randomly flip the image either horizontal or vertical. It's random, of course. A preprocessing layer which randomly flips images during training. This layer will flip the images horizontally or vertically based on the mode attribute. There's a bunch of other ones. It's a lot actually. So we can do layers like random zoom. We can do 0.1. So this will define how much we want to zoom it, but it'll still be random. So it says a preprocessing layer which randomly zooms images during training. This layer will randomly zoom in or out on each axis of an image independently, filling empty space according to fill mode. The 0.1 corresponds to 10%, so it's going to zoom within a range of 0 to 10% in or out. So it can zoom in up to 10% or zoom out up to 10%. That's why it's random. It can choose the number and also the direction. Here's a few more. So I have random brightness, random contrast, random rotation. So as the numbers imply, sort of, the higher the number, the more radical these changes are going to be. So if you change this to be 0.5 instead of 0.1, it's able to rotate a lot further. I would say start low though, and then tweak upwards, just because if you change it too much, your images may not be sort of distinguishable from the other samples that you have. So just make sure to play around with that, just like always. So that's all the data augmentation layers I'm going to add. There are more that we can add, but those are some of the most common ones. One thing that we can do is actually move resizing into this as well, because that technically is augmenting the data. So we could do layers dot resizing, and we could do 256 and 256 just like we did down here. So now every time we feed an image through these layers here, first it's going to resize them to that standard range of 256 to 256. It's also important that we put it in front of these because, of course, we don't want to resize after we do all of our changes. So we want to resize and then do our augmentations, right? With that said, the other thing that we want to move after the augmentations is this, which is casting it to a float data type and also dividing by 255. We already knew this, but we can add another layer for that. So layers dot rescaling instead of resizing, rescaling, and then 1.0 divided by 255.0. So what this will do is convert it to that floating point data type and at the same time change it to the range of 0 to 1 for all the pixel values. So this is something that you want to do after you've done all of your changes, but resizing is something you want to do before all of your changes. So now for our training set, we don't want to use the preprocess function to map our values, right? Because this is not the only two things that we want to do now. We also want to do all of these things. So for our training set, let's remove this and let's replace it with a new function just for our training set. And this will take in the same thing, an image and a label. And it's just going to return data augmentation and then image and then label. So what this will do is take our image, pass it into our data augmentation layers. So it'll do all these changes here, spit it out, return it along with the label. So now we still have our tuple of our image and our label, except that the image has been modified. So now when we call the map function on our training set, we can simply use our augment function instead. So to be clear, all the augmentation that we're doing should only be done on the training set. It's not necessary to augment the validation or testing set because we want it to be unseen data, just normal unseen data, right? If you wanted to, of course, you could change this to use the sequential layers as well to be a little more consistent. So you could do Keras.sequential and just have resizing and then rescaling. That's really up to you. I'm just showing you two different ways of doing something. But for this one, since we're doing all these transformations here, these augmentations, it makes sense to just use the layers before and after. All right, so with all those changes in mind, we should be good to go now. So let's go ahead and just try it out. So currently, just as a reminder, our accuracy is roughly 64% and our loss is around 92%, okay? So let's try this out. So while this is taking 45 years to train, I just want to kind of explain what's happening here. So I mentioned before in the beginning that whenever you do data augmentation, it's going to artificially increase the size of your data sets. So currently here we have our layers, right, that do the data augmentation, these ones specifically. The question is, when we actually map this onto our data set, is it actually changing the images or adding new images? The answer is neither technically. If you check the size of this dataset before and after the mapping, it's still going to be the same. You're still going to have your original images. But what will happen is that whenever you actually train the model and the model is doing prefetching or grabbing the next batch or something like that, then it's going to apply these layers to that batch. So every single epoch, what it's going to do is apply these layers to the images that you have. and then obtain new random images. The reason for that is because we have all these transformations, right? And if we were to apply these onto the images that we already have and the data set's very large, then we would just increase our data set, potentially a lot, like a lot, and that could really overload our memory, right? So storing that is a problem, of course. So dynamically transforming these images as we need them when we're actually doing the training makes more sense. So I'll say it again, every single epoch, we're going to grab all the images, right? Every single time you grab an image, every single epoch, it's going to automatically apply all these transformations and give you a new randomly augmented image. Because of course, it's random flip, so it's going to randomly choose whether it wants to horizontally or vertically flip it. Random brightness is going to choose how much brightness we want to do, up to 10%. Same for these as well. So every epoch, you're going to get a new image without actually having to store the image in memory, which is much more efficient. All right, guys, look at this work of art right here. It's done training, and we can see that. Let's just scroll down all the way to the test accuracy, almost 80%. So we went from literally 63%, 64% to 80%. That's crazy. And then our test loss went from about 0.93 to 0.59. That is a huge improvement. With some data sets and some models, you may squeeze out a couple of percentage points, but for this one, we've increased our accuracy and our loss dramatically. And we're doing all of this just from data augmentation, which is even more impressive. Now, the thing is, though, this took 33 minutes. Yeah, 33 minutes just to go 29 epochs. And that's also crazy, by the way. We went from 8 epochs to 29. That's even more impressive. The reason that it's taking so long is likely because we're doing this all on the CPU currently. That's because we're calling the map function and calling augment on our dataset, and this is then calling the transformations, right? Even though these are layers, because we've integrated them not directly into our model, but into our data pipeline, it's going to use our CPU, which could take longer. So another option that you could do is integrate these layers directly into your model. All right, so to do the data augmentation directly in the model, all we got to do is use this variable here directly in the model. So we'll go here and do data augmentation like that. So now all these sublayers here will be directly placed into the model. So when the input goes into the model, we'll go through those layers first, and then finally onto our first convolutional layer. But we have to make a few changes for this to actually work. First, we want to get rid of these augment and preprocess calls because we are now calling all of this when the input goes into the model, right? So we no longer need to do the data augmentation directly in the, the data preprocessing pipeline. So we can comment this out and remove augment. But now, since every single input of the model, no matter what set it comes from, will be going through these sublayers here, we should also get rid of this preprocessing function call here because now we're going to be doing it twice, right? So it's going to resize it, rescale it, and then send it into the model, and then the model is going to try resizing it, doing all these augmentations, and then rescaling it. Obviously, we don't want to do that twice, so we should get rid of these as well. So boom, and then boom, like that. Another important thing, though, is that we don't want to do data augmentation for anything other than the training set. Like I explained before, it's only for the training set to make the training set more robust and improve the model performance during training, right? But for the validation set and the test set, this is just going to be our normal data, so we don't want to augment that. The great thing about Keras, though, is that during training of the model, it will now automatically not use these data augmentation layers here. So it won't do the random flip or the random contrast, but it will do the resizing and rescaling, because that's just normal preprocessing. Another issue that we have to address is that whenever you try compiling this model, you're going to get an error because it no longer knows what the input shape will be, and the model has to have a consistent input shape. Before, that wasn't a problem because we were just running these sublayers here directly on our preprocessing pipeline, but now since this is our first layer and not this here, it doesn't know what that input shape will be. This is obviously going to accept a bunch of different input shapes because the whole point of this layer is to resize them to a consistent input shape. So that's unfortunately just a problem with this type of setup. Like I said before, the model expects a consistent input shape for the spatial dimensions. So just one way to get around this is, first of all, let's go ahead and define that input shape right here. So we'll do keras.input and then do shape is equal to, and then we'll do 256, 256, and 3. So that will help the model understand what the input shape will be. But then now we just want to go ahead and get rid of this resizing layer, and we'll just move it back to our preprocessing function. So now the preprocess function will do the resizing, and then we'll just comment out the rescaling part because that can still be done directly within the model. So now we'll add the preprocess call back to all three of these. So with that change, all the input that goes into the model will all have the size of 256 by 256 by 3 because we are preprocessing the data before it ever goes into the model. And so that fixes that issue of the inconsistent shape size. So this should still be a huge speed up because we're now running all the data augmentation and the rescaling directly on the GPU. The only thing that's going to be remaining on the CPU will be the resizing, okay? So I know that was probably a little confusing, but hopefully that makes sense. Just make sure to, of course, check the code in the description below so you can play around with it yourself. But that's all the changes that we need to make. So let's go ahead and try running it finally and see if we get the same results and if it runs faster. All right, look at this work of art here. So it's done training. It took, 40 epochs, which is a lot of time, which is great. And it got up to a training accuracy of, it looks like, very close to 80%. But looking at our test accuracy, we can see we have, 80%, and then a test loss of 0.55. So pretty much the exact same results that we got with the model running on the CPU with preprocessing. So that's really, really good. The difference, though, is that, as you can see, this cell here, we did the training, only took 7 minutes versus, 33 minutes? So that's a huge speed up, and that's all thanks to our GPU that we have available to us on this, notebook here. So that's pretty much all I want to show you. As you can see, data augmentation is a very powerful technique that you can use to improve the results of your model and also serve as a regularization technique because it does fight overfitting as well. With this dataset especially, we were able to increase the quality of our results by a lot, which is awesome. So the last question would be, should I run these data augmentation layers here on the CPU using tf.data as we did the first time? Or should we do it like this, where we run them directly on the GPU? So of course, this is going to be case by case, but if you have a less powerful CPU as we have, then obviously running it on the GPU will be much faster. We saw that there was a great speed up when we did that. But sometimes you may have a very capable CPU, so running it on the CPU may free up your GPU for other resources. The other thing is that sometimes your data preprocessing pipelines are going to be way more complex than what we're doing here. So sometimes it'll make more sense to run it on the CPU because sometimes if it's too complex, running all that in the GPU doesn't make a whole lot of sense. That's going to fry your GPU or slow things down a lot. So it really just depends. But overall, I think just understanding the differences between both approaches is really great. So whenever you find yourself in a specific situation, you'll know what you can do, what your options are, okay? So hopefully you guys enjoyed this video. Hopefully you guys learned a lot. I found this to be really cool and I learned about this myself. Now you guys should know how to do data augmentation. Awesome. See you guys next time. Peace. So that's it for this video, everybody. I really hope you learned something new. If you liked the video, please hit the like button, and if you want to see more, hit that subscribe button. Make sure to also check the description below for important links to code and other resources, but also really important, join our Discord. We have a big community of over 5,000 programmers, and it's a place where you can find new friends or get help on any code that you're stuck on. If you want to support what I do on this channel, please consider hitting the join button below, and this will allow you to support my channel for as low as $1 a month, but there are different tiers to choose from if you want to. For anyone that becomes a member on my channel, you get a special rank on my Discord server, early access to new videos, and you can just see yourself on the screen right now. So if that sounds cool to you, feel free to join. If you don't want to, that's fine. If you can't, that's okay too. I really just appreciate you watching the video anyway. Thank you so much. And that's it. Peace.